Welcome to our next day of workshop. So today is Wednesday, and we have our first speaker, Mikito Nanashima. He will tell us about learning and pseudorandom generators in constant parallel time.
Thank you for coming this very early morning talk. So today I'm going to talk about relationships between learning and pseudorandom generators computable in constant parallel time. And this talk is based on joint work with Shuichi. Okay, now let's get started. So in this workshop, we have already seen, or maybe we will see, many beautiful relationships between learning and pseudorandomness. So generally speaking, roughly speaking, the learning is a task to find hidden information in the observed data. By contrast, pseudorandomness is pseudorandom string is a string indistinguishable from a truly random string, but generated from a very short seed. So now, if we consider this learner as an adversary that tries to distinguish the pseudorandom string, and if we regard hidden information the learner tries to learn as a random seed to generate a pseudorandom string, then these two goals say kind of opposite things. So that's why in a certain regime, maybe we cannot hope for both simultaneously. Then the desirable situation here is to guarantee either at least one of efficient learning or secure pseudorandom generator. And this year's win-win argument. And this question is rephrased as whether we can obtain the equivalence result between hardness learning and the existence of pseudorandom generator. And so in general case, fortunately, the answer is yes. So particularly one direction from pseudorandomness to hardness learning dates back to the very first paper by Variant in computational learning theory. The other direction is by Impagat-Levin and Bram, Frost, Ganz, Lipton, and many other folks. And so to show the opposite direction, they often consider average case variant of hardness learning. Particularly in the previous work, BFKA, they proposed one very natural average case variant of PAC learning. So now I explain this model. So the target of learning is a concept class as just usual PAC learning, and which is defined as a subset of Boolean valid function here. And in this average case variant, so we consider two distributions. The first one is distribution over functions in the class. More precisely speaking, so this is a distribution over a representation of functions in the class. And the second distribution is usually called example distribution. This is a distribution over input to the functions in the class. And so in this average case variant of PAC learning model, so we consider weak learning for class C as follows. So the learner is given a sample set. So input-output pairs for target function the learner tries to learn, where this target function is selected according to this distribution F. And each input to the target function, this is usually called example, is selected according to this example distribution. And this learner is also given an unlabeled data challenge. And this challenge is also selected according to the same example distribution. And the task is to find the label of this challenge with non-negligible probability, better than random guess. And so I mentioned that, so we usually call this M, the amount of samples the runner requires as sample complexity. And in this model, we can characterize the existence of pseudorandom generator. So the existence of pseudorandom generator is characterized by average case hardness of weak learning in this model for some polynomial computable class C with respect to some probability distribution F and D. So we consider very general learning setting, then we can characterize the existence of PPRG. Okay, great. Then, okay, let's move on to the next question. Learning a simple class versus pseudorandom generator computable in simple class. Actually, this question is motivated from both sides. So from one side, so from the existence of pseudorandom generator to hardness learning simple class, it's usually demonstrated as a cryptographic hardness of learning to identify the capability of efficient learning. And so I will explain later the recent work in this research direction. And the other direction from hardness of learning to pseudorandom generator in computable in simple class is motivated by efficiently performable cryptography, whose security is based on hardness assumption of learning. Particularly in BFK, so this motivation is also mentioned, and they propose one candidate for pseudorandom generator computable in polysize DNF based on some average case hardness of learning. And in this talk, in this work, we consider one of the simplest cases in pseudorandom generator part. So we consider the relationship between average case hardness of learning and existence of polynomial-stretch pseudorandom generator computable in NC0. In short, PPRG in NC0. What is this primitive? So PPRG in NC0 looks like this. So this is polynomial-stretch pseudorandom generator. So it is given an n-bit random string, then it stretches it polynomial larger pseudorandom bit. But point here is, so this primitive must be computable in NC0. So it means that each pseudorandom bit only depends on constant number of randomness. And so this primitive is really important for several remarkable applications. And point here is, but constructing PPRG in NC0 is relatively harder than constructing other cryptographic primitive in NC0. In the sense that, so we do not have any known construction based on the self-related work on randomized encoding. Because to apply randomized encoding, we need additional randomness. And of course, the same amount of randomness will be outputted, but it drastically decreased the stretch of pseudorandom generator. So that's why, based on randomized encoding, we do not have any construction based on the construction of PPRG and NC0. And so previously known construction for this primitive is based on one framework, Goldreich one function, Goldreich PRG. It is, so this is a generator specified with fixed predicate P and input output connection, and it defines some generator. So we have a random seed, and for each input output connection, we look at the corresponding part and we apply this fixed predicate. And so previously known candidate for PPRG and NC0 follows this framework with good choice of fixed predicate P and input output connection. Yeah.
So can you say again what's the problem with randomized encoding? Is it a stretch? Or can you say it again? I didn't.
Okay, so to use randomized encoding, so the purpose of randomized encoding is to reduce the complexity class computable NC1 to NC0 or something like that. But to reduce the complexity class, we need additional randomness, and we encode some partial computation by using the randomness. But so if we add additional randomness, then and of course the same amount of randomness will be output. But this additional randomness decreases the stretch of the original pseudorandom generator. So yeah, even if the original pseudorandom generator, for example, polynomial stretch. So when we add some polynomially many additional randomness, then the stretch becomes sublinear or something.
Even with linear stretch.
Yes, yes, yes. I also want to mention that, so when we consider pseudorandom generator in NC0, it is standard to consider some relaxed requirement, correction of PPRGs in NC0. So difference between correction PPRGs in NC0 and standard PPRGs is just so in correction PPRGs in NC0, we consider at the initialization step, the description of generator is selected according to some generator of generator. So by using a public randomness, but we do not care about this complexity. So this G might be not computable in NC0, but the output generator must be computable in NC0. And so we consider this type of generator because this is relatively easier to construct than fixed PPRG in NC0, but it does not affect the application so much. And it,
You need the good and balanced expanders for such local PRGs. Even if you pick a collection, it doesn't make the problem go go away. I mean, there is the work by Applebaum that shows how to fix such expanders. But my question is, technically, do you care about some inverse polynomial failure probability of the PRG, or you don't care about it? But
Sorry.
I'm just saying that such a PRG necessitates a good and balanced expanders, which we don't have explicit constructions. But this is one reason why if you pick a graph at random, then with inverse polynomial probability, it will fail to be a PRG because it doesn't have the necessary expansion. So is this an issue or not an issue?
So yeah, so of course we have some definition of distinguishing. So we take into account the randomness reflection in the advantage of distinguishing. So that's why if we fail selecting good expander with non-negligible probability, maybe can easily distinguish because we also take into account the randomness.
Yeah, anyway, it's typically not an issue because we can either, yeah, I was just wondering if it makes sense. So we just assume that that such a collection exists and that's it. You don't yeah.
But okay, in this one, we need to, this random selection is really important. I'll explain later the reason. At least in this one, we need to consider this random selection.
Yeah, but so the random can be taken from any distribution. You don't care about the distribution of the collection. But again, in the following, you don't care about how you pick the random PRG, just assume it to be taken from some distribution, right? Just to make sure.
So maybe
Okay.
Okay, I am. Okay, and so yeah, again, so in this one we consider correction PPRG and standard PPRG. Okay, and so let's go back to the relationships okay, so again, so if we select this input output connection at uniformly at random, then it is kind of correction PPRG. And even in this one, we also consider correction type of PPRG analysis. And so let's go back to the topic about the relationships to learning. And so as far as I know, the previously known relationship between PPRG and NC and learning is so only one direction. So if we have PPRG and NC0 or some related notion, then we can show hardness learning for very simple class. For example, in the work by Daniel and Buddy, they show that hardness of learning for several important classes based on the existence of poly-stretch pseudorandom generator. And in this work, we consider the exact relationship. So equivalence between so characterization result for correction PPRG and NC0 based on average case hardness of learning. And if we can show this, so we can so it enables a new learning theoretic approach to construct PPRG and NC0 by using reasonable, seemingly correct hardness assumption of learning. And so by the very well-known equivalence result between unpredictability and pseudorandomness, so some of you might believe so conjecture that so this primitive is captured by the hardness for NC0. I think this is really a natural conjecture, but this natural conjecture seems to be incorrect because in cryptography, so constructing correction PPRGs in NC0 is a central challenge. By contrast, so learning NC0, it is usually called learning constant pointer, is trivially learnable by using Occam's razor. So this learning part does not hold unconditional. Then the question here, so that's why, so when we consider a very low complexity class, like as a NC0, the dichotomy between learning and large stretch pseudorandom generator seems to become very non-trivial. Then the question here is still, can we obtain the characterization result for such a PPRG and NC0 based on hardness of learning? Okay, let's see our results. The question here is, so can PPRG and NC0 be characterized by learnability? The answer is yes, by considering a fixed parameter tractable sample complexity. So in this work, we consider a parameterized setting of learning. So we consider parameterized concept class C and parameterized class of distribution. And we consider FPT sample complexity written like this by using some computable function F. But so point here is in this work, we consider FPT sample complexity, but we do not consider FPT time complexity. The time complexity can depend parameter. So in other words, in this work, we consider the situation in which collecting samples takes much more cost than consuming computational time. And it is still natural setting for us. But so even if we consider fixed parameter tractable sample complexity, the problem does not become so easy. So particularly learning k-filter, where the k-filter is just function, which depends on only at most k-relevant coordinates. But anyway, so learning k-filter is still learnable with FPT samples. So to characterize PPRGs in NC0, we seems to consider the need to consider some non-trivial learning setting. Then what is the equivalence result? First of all, we have a general relationship between pseudorandom generator and average case hardness of weak learning. And we obtain the existence of the characterization for correction of PPRGs in NC0, we tune up these three settings. We consider average case hardness of weak learning with FPT samples. And the concept class is C sparse F2 polynomials. And the distribution over functions is samplable by a depth the NC0 circuit. And we consider example distribution as samplable and C prime sparse one, where the meaning of C prime sparse is the Hamming weight of string in the supported support of Z, so D is bounded by this C prime. Then we can characterize by using this learning setting. We can characterize the existence of PPRGs in NC0 informally. But technically speaking, to characterize a collection of PPRGs in NC0, we also need to consider initialization step even for this learning setting. So we must, technically speaking, we need to consider samplable with shared randomness. The difference is at the initialization step, we select shared random, public randomness. Yeah. And the shared randomness we will shared during the sampling process. But we can, and this part just makes easier to hold the assumption, makes the assumption easier to hold than fixed example distribution. So from the perspective of cryptography, this is more difficult to construct collection of PPRGs and NC0. And this is the first equivalence result between collection of PPRGs and NC0.
Sorry, can you help me understand? So C is the concept class, F, what is F?
Yeah, distribution over functions. I mean, so distribution over representation of C sparse F2 polynomials. And D is example distribution. Sorry.
So I'm generating the samples by one of these objects.
So by using D, we generate samples, so input parts. And by selecting F, we can construct labels.
So there is a hidden sparse polynomial, and what are these labels? Labels are computed by what? By circuits? I'm confused how F and C relate.
So okay, so
again, also FPT is about what? Is FTB in
FPT
C?
is for also the parameters are this C and this D, and so this C.
Okay, all of them. Okay.
All of them, yes.
And can you explain again what is C and F? How do they play a role?
Sorry.
Can you again explain how C and F play a role here?
Okay, so F select a function contained in this class C. So this F selects a representation of C sparse F2 polynomials.
Okay. Okay. All right.
Yeah. Can I ask for some more information about the learning problem here? How does it relate to learning problems I'm already familiar with? How does it compare?
I realize that this is an equivalence. I'm just trying to place this in the realm of things that I know.
So you mean the running business, the no harness of running.
Sorry?
So
just intuition about the learning problem. How should I think? Easy, hard, is it similar to something I thought of before? But,
yeah. First of all, if we believe the existence of PPRGs and NC, then this something so. But so okay, it contains very natural. As I explained, but it contains a very natural running program. It is somewhat related to the question whether we can implement Goldberg algorithm without membership question. It is somewhat related to running party with noise or something like that. So yes, it has some connections with previously well studied running.
I understand it correctly that this problem is related to learning parities with noise?
No. Yeah, it is just related. So, so we cannot show direct connection, but so maybe I will explain later the natural settings, and then I explain the
Just again, a question about the statement. So, in terms of preserving hardness, if the learning problem, say, is 2 to the square root hard, the PPRGs will be comparably hard or quasi-polynomially hard. What is the level of hardness?
Okay, so the security loss is just polynomial. So if we assume polynomial, so.
And again, in terms of the expansion thing, so maybe it will be understood later, but we can cover by the syntactic fact that the collection of PPRGs in NC0 implies the construction of good, the randomized construction of good expanders, which is non-trivial. How is this reflected on the
So yeah, so maybe we consider such a non-trivial construction in this example section of examples.
A super basic question, if that helps. So maybe intuitively the reason why we should think, you can answer no. Maybe intuitively the reason why we should think that this concept class is hard to learn is because like the Goldrake one-way function and generator is like, you know, randomly sampling some inputs and then applying like a sparse F2 polynomial to them. Like, is that sort of the right intuition here?
Yeah, maybe. So you mean so? Oh, so you consider Goldrake one function for sample?
Yeah. Yeah.
I think this situation is really different here.
Oh, really? Okay.
For example, so particularly when we consider collection PPRGs based on this framework, the predicate will be different.
Oh, it will be. Okay. Okay.
And so this is a characterization result for PPRG and C0 based on harness running. And we can also obtain the same characterization result for several concept classes, like the C phrase plus function or Dix departition to That's what I asked. And so, yeah, I have already explained this part, but this result was even in super polynomial with polynomial security loss. So if we assume sub-exponential average case hardness of weak running, it gets a sub-exponential secure PPRG and C0. And so by using this theorem, so if you specify F and D satisfying these constraints, and if you believe the hardness of running, then you can construct collection PPRGs in NC0. So it enables a new running theoretic approach to construct collection of PPRGs in NC0. But the weakness of this theorem is, this theorem itself is very general characterization result. So it does not specify any F and D. So that's why finding good candidate for all these F and D seems really important and interesting. Okay, and so, but in the original work, we propose one very natural candidate test case for this setting. One is so running random parity decision trees. Yeah, in fact, this is a really similar problem to learning with noise, but the difference is the noise will be computed by some other parties. But anyway, so running random parity decision trees. So this is look like this. So for each internal node, we ask parity on random subset, and each leaf is labeled by some random value. And so hardness of this concept, this random function, seems consistent with our current knowledge. And if this problem is uniform, so hard on uniform example distribution over slice, then it yields a secure correction of PPRGs and C0. But there is another reason for importance of studying this problem. So if this problem is even hard on uniform example distribution, it still gets a very simply computable pseudorandom generator, a single PPRG computable in parity NC0, where we are.
Anytime you say learning on the screen, you mean FPT hardness every time, or like here you said learning random learning distributions. You mean FPT samples?
I think so.
Yeah. Okay.
And so if this problem is hard on uniform distribution, then it has a single PPRG in parity NC0. Even if this problem is hard on general sample distribution, it yields correction PPRGs in parity NC0. So in either case, the hardness of random parity distribution trees yields very efficiently computable with PPRG.
So by parity NC0, you just mean a constant degree polynomial?
Yes, yes,
okay,
exactly. Okay, and in this work, we've also considered several related problems. So, for example, so in the previous characterization result, we consider we assume sparsity of data. But what if we remove this sparsity of data? Our technique for showing the equivalence result still gives a dichotomy between learning and pseudo-randomness. For example, so if C-sparse learning C-sparse F2 polynomials on distribution samplable by C'-sparse F2 polynomials is hard, so we consider general samplable distribution without sparsity of data. Then we can obtain the existence of correction. We can obtain correction of PPRGs computable in constant sparse F2 polynomials. And if we consider samplable distribution with shared randomness, we can characterize this correction PPRGs. And we can also obtain the same result for C Fourier sparse functions. And the second, so in the previous characterization result, we considered correction of PPRGs. But can we obtain the dichotomy between learning and a single PPRG computable in some simple class? The answer is yes, by considering, okay, so parity NC0. And so, yeah, this is actually equivalent to constant degree F2 polynomials. And so we can characterize single PPRG computable in parity NC0 based on average case hardness of learning for degree D F2 polynomials on distribution samplable by a degree D prime F2 polynomials. And we consider uniform example distribution. And we can also show that, so if we change this uniform example distribution to general samplable distribution with shared randomness, then we can also characterize the existence of correction of PPRGs computable in the same class. So in other words, we can characterize the difference between single PPRG and a collection of PPRGs in the class parity NC0 by using the difference between the generality of example distribution in the hardness part, the uniform distribution or samplable distribution with shared randomness.
Take, for instance, just PRG, but defined by random quadratic polynomials, which is a kind of a semi-standard cryptographic assumption. What would this correspond to? If you just look again at the PRG, where each output is a random quadratic polynomial.
Oh, and the difference to run.
Just to illustrate the connection, like if you take this example on the right, what would this correspond to?
Yeah. This, sorry, actually. Also, maybe you so PRG based on others. But yeah, actually this part is almost Yeah, just we select randomly function and evaluated it. But to guarantee, so to obtain polynomial storage, we need some trick using some synthesizer or something. But yeah, maybe your interested.
Sorry, when you say strong here, is there what people also call proper learning? That what you output has to be in a certain class?
Sorry?
When you write strong learning in the slide, is that also what people call proper learning?
So 1 minus, so with accuracy with 1 minus some small constant. In previous characterization result we consider weak learning, it means that so with so accuracy 1/2 plus some non-negligible factor or something. But here we can consider yeah.
So it's the standard original pack definition, as opposed to weak learning, which is a relaxation.
Yes.
Just saying.
But we consider yeah, yes.
Did you get your answer, Manu?
Okay, so and now so let's go back to the first result, characterization result for collection of PPRGs and see that because this is I think the most remarkable result in this work. And I explain how to so that proof technique for showing this theorem. And the idea to show the characterization result is to use dualization. And in this work, we formally define the notion of dualization of a concept class C by two easily computable functions G and H looks like this figure. So the role of one function G is to map each representation of function in the class to some string f star, and we call this the dual of f. And another, so the role of another function h is to map each string to representation of function x star, and we call this the dual of x. And constraint here is for every function in the class and for every input, the evaluation of this function is equal to the evaluation of the dual. This is the constraint. And the meaning of easily computable depends on the target. So theorem we try to show. And in the case of PPRGs in NC0, this must be computable in NC0.
So like, for example, if you have a fixed pseudorandom generator, so we're thinking of, to make it a learning problem, we think of the input as a bit position. And so, and then the function is given by the seed.
Yes.
And so now you have like some definition in the pseudorandom generator that says, how do you look up the bits of, which bits of the seed do you access? And then how do you compute the function? And all of that is going to be the X star that says which bits of the seed do you look at and how do you compute the ith bit from this, right?
Yes.
Okay.
Maybe you now explain the yeah, sure, that's right. I will explain later. Yes. Okay, so. Okay, so first of all, so let's see the example for this dualization. So let's see the case of D parity decision tree, but the idea is really simple. So let's assume that so the representation is just this A's at the internal node and so each level, and input is X. And so for just so yeah, so we can regard this part as just taking some inner product with very trivial way, and so yeah, we add one additional leaf. And then we can regard, so by regarding this representation as input, and we can also regard this X is a representation of parity addition rate. This is a very simple idea to taking dual D parity addition rate. Yeah, of course, we need to add some proper pattern to obtain varied representation of addition rate, but this is very rough. explanation, the dual of the party distributed. Okay, again, so the reason why we consider dualization is so first of all, in general, so to connect the notion of learning and the connection notion of cryptography, so we need some kind of dualization notion in the sense that so in learning, the public information is input to the function, and secret information is a function the learner tries to learn. By contrast, in cryptography, the public information is a function that tries to compute the primitive, like a Bayesian function or pseudorandom or something like that. And secret information is a random seed input to the function. And to connect these two notions, we need to switch the roles of input and function. And if we have the explicit dualization notion for a concept class I defined in the previous slide, then we can do this switching very trivially. Particularly if we have dualization of a class C, we can connect the hardness of learning C and pseudorandom generator computable in C very easy. So first I explained the rough idea, rough outline, then I explained the details for PPRGs and NC. Okay, first, so let's consider the direction from hardness learning C and pseudorandom generator. Then we can easily sample unpredictable sample set in this hardness program. Then by taking the dual of this sample set, we can obtain some pseudo-random generator object, each object, where each input is changed to a function by taking dual. And the target function f is changed to C to this generator. And each output bit of generator corresponds to each label. And the pseudo-randomness of this generator follows from the equivalence between pseudo-randomness and unpredictability. But technically speaking, this is not pseudo-random generator because so this dual of f is not distributed uniformly in general. But as I will explain later how to change this to pseudo-random generator. And I also want to mention that so this is actually a collection of pseudo-random generator because to obtain the description of this generator, first we need to select sample according to this example distribution, and we must select. So we must compute the dual of the sample. That's why this is actually a collection of pseudo-random generator, each object. Okay. And so for the so other direction from pseudo-random generator computable in C to hardness learning C. So if we have a pseudo-random generator, then by taking the dual of this, we can obtain, again, so unpredictable sample set, where the target function is a dual of random seed. But so to show hardness of learning, we consider uniform distribution over samples, but it yields only hardness with fixed sample complexity. If the learner does not look at the whole input, then we can show the hardness of learning. So it yields a hardness of learning with fixed sample complexity. So I explained later how to enhance this to FPT sample complexity. So now I explain the details. But how to change this pseudo-random generator each object to pseudo-random generator? The idea is very simple. So we also contain the random selection of function and the computation of dual as a part of pseudo-random generator. Then we can obtain pseudo-random generator. The seed for the sampling is just random. And by taking enough, so large enough sample complexity, so by careful observation, actually in our case, this is so FPT sample complexity is sufficient in our case. So by taking sufficient large sample complexity, we can obtain polynomial-stretch pseudo-random generator. And the complexity to computing this pseudo-random generator is just the composition of class C. We consider about dual and the complexity of computing dual and complexity for sampling function f. And in our case, this is NC0, and so we also consider NC0 sample distribution. So if this part is NC0, then this must be computable in NC0. Okay, and if so, we have this. So okay, so the next problem is how to extend this result to fixed parameter sample complexity. But the idea is very simple. So just we apply GZM construction. And we also use the assumption polynomial-stretch. So in GGM construction, so we again and again apply the original generator to enhance the stretch of the generator. And if the original generator is polynomial stretch, the number of applications affects exponent in the stretch. But it also increases the parameter of for computing pseudorandom generator. And by taking the dual, so it also increases the parameter for running the problem. Then the learner tries to look at more samples. But when we consider FPT sample complexity, this increment only affects this number of applications only affect multiplicatively for number of samples the runner requires. That's why, so by taking large, so sufficiently many applications, we can prepare enough sample sets to show hardness run with FPT sample complexity. That's why we can connect with FPT sample complexity and the existence of collection of pseudo-random generator. And if we can show dualization of, so that's why if we can show dualization of NC0, then we can characterize so the existence of collection PPRGs and NC0, but by using hardness of running NC0. And this seems to be incorrect conjecture. So, and actually, unfortunately, we cannot hope for dualization of NC0 or K filter. So we cannot construct this type of dual. So K filter is mapped to some string and some string is mapped to K filter with preserving evaluation. And so this is because roughly speaking, evaluating K filter requires constant number of bits bit information of the representation of F. And we can justify, so verify this by using the augment on communication complexity. So to sum up, if we have dualization of some class C, we can connect the hardness of running C and the existence of PPRG is computable in C. But we cannot hope for dualization of NC. Then how can we use this idea to show the equivalence result to PPRGs in NC0? The idea is to use dualization of superclasses of NC0. So for now, so first, let's forget about NC0. And so assume that so we have some dualization of superclass of NC0. But because this class is superclass of NC0, so funta must be contained in this class. And this part must be mapped to some subclass of strings. If this subclass is again mapped to funta, then we can use this dualization of superclass of NC0 as a kind of pseudo dualization of NC0. And actually, in our case, this subclass is sparse strings. So, and we define the notion of funta sparse condition of dual. So in the dualization, the funta part it will be mapped to some sparse string, and each sparse string is mapped to some funta. And by using dual with funta sparse condition, we characterize PPRGs in NC0 based on hardness of learning on sparse data, sparse distribution. Because, okay, so this is the previous slide. And so let's consider hardness of learning on sparse data. Then this part is sparse. And by taking the dual with funta sparse condition, this part becomes NC0 funta. Then we can compute this pseudo-random generator in NC0. And if we have pseudo-random generator computable in NC0, so this part must be funta NC0. And by taking the dual with funta sparse condition, so we can again obtain hardness of learning on sparse data. So we can characterize PPRGs in NC0 by using hardness of learning on sparse data. And this idea is Meta-Theorem for the first term. So we define the notion of FPT dualizable in NC0 with funta sparse condition like this. So we have two NC0 computable functions such that so it satisfies the condition of dual. And every K funta must be contained in this class. And the dual of K funta is sparse string. The Hamming weight is bounded. And for every string with fixed, so every sparse string, the dual of sparse string is K funta in this. For example, so we can verify that actually the previous example for dualization parity decision tree satisfied this condition. So roughly speaking, this is because so let's consider so input as a sparse string. Then at each internal node, we only look at constant number of inputs. So this is and vice versa. Okay, and we can show Meta-Theorem. So if parameterized class is admits this dual notion with Funta sparse condition, then we can characterize collection of PPRGs in NC0 based on the average case hardness of this class with respect to C-sparse distribution and NC0 samplable distribution over functions. And by verifying so that these classes satisfy the condition, this condition, then we can show the first result based on this Meta-Theorem. And the importance of this Meta-Theorem is yes. So by using this Meta-Theorem, we can reduce the task of characterizing collection of PPRGs to just study on representation of Boolean function, because finding or verifying dualization with Funta sparse condition for some class is really puzzle-like problem on the representation of Boolean functions. So if you have your favorite class, and if you can verify this, so you can solve some the puzzle problem, then we can obtain dichotomy between PPRGs in NC0 and learnability for your favorite class. And actually, to show this, you do not need anything about learning or pseudorandom. Okay. And in conclusion, in this work, we consider dichotomy between learning and pseudorandom generator computable in very low complexity class, particularly in NC0. And we obtain the first characterization result for such a class. And actually, this theorem follows from Meta-Theorem, where we consider the notion of dual with Funta sparse condition. Then there are several future directions. The first one is finding other characterizations for other class by using this Meta-Theorem. And it is also interesting to find some other useful substructure than Funta sparse condition. And by finding this, it might be possible to characterize this notion by using other interesting class of example distribution. And so other direction is finding good candidates for DNF to construct PPRG in NC0 and further analysis of random parity distances. Okay, that's all. Thank you very much.
Questions?
So this is getting off topic a bit, but this notion of dual is somewhat interesting. So it seems like one way to bound the complexity of the dual problem is to show that the circuit evaluation problem for the class is in the class itself, because then you can use that for both the circuit evaluation is kind of like a self-dual problem. But maybe there are some ways of coding information. Are we like allowed to recode how inputs are described and also how functions are described arbitrarily in order to lower the cost of circuit evaluation? Is there some characterization of the complexity of duals in terms of some form of circuit evaluation?
Yeah, that's very. I have not considered it. Oh, sorry, I'm not considering it. I have not any preference.
And less posing this as a question just to you, but a question to everyone.
This question has been, at least that I know, it's been studied a little bit like with the IPPP conjecture with AC0 on top of non-2 gates. Which is kind of considered like pre-processing then, but with linearly trying to compute. So
So specific examples of how to redefine. I'm wondering if there's like some generic way of doing it.
Thank you. Other questions? Thank you. Reconvene in like 10 minutes.